2. This is the last talk of the summer, so we're almost free. So yeah, before I get into part 2, I wanted to quickly mention some useful resources. So if you're really interested in reinforcement learning, the best place to start is the classic book by Sutton and Bardo, Reinforcement Learning and Introduction. So the print edition is quite old, and everything in it still applies, and it's still good to read, but it's a little outdated. So I think Rich Sutton is working on the second edition now, and the latest draft is actually available on his website. I think he posted an update last week, so it's really fresh. So a slightly more rigorous treatment of standard algorithms can be found in Algorithms for RL from Csaba Szepesvári. So that's slightly more mathematical, and it's also available online. I think another great resource is David Silver's UCL course on reinforcement learning. So the slides and videos are available online, and actually a lot of the background material I've been covering has been basically borrowed from this course, which I should have mentioned. So yeah, let's get back into it. So yesterday we mostly talked about value-based methods, and in particular Q-learning. So with Q-learning, we can learn optimal value functions and MVPs under certain conditions. So why would we need anything else? Isn't this the end? Well, in practice, you know, you can't just apply it and get the optimal value function for any MVP. There are issues like exploration and practical issues like maybe the action value function for your problem is very difficult to learn, right? Very non-linear. And also to do Q-learning, you have to do this maximization of actions in Bootstrap. So you might have a very high dimensional action space, so that might actually be different. And also you might have a continuous action problem. So then how would you do Q-learning? So there are methods, but maybe there is another approach. And as I mentioned yesterday, policy-based methods are basically an alternative. So as we saw in some of the examples, there are a lot of states where the precise actions don't really matter. Maybe we're wasting effort trying to learn the optimal Q values in all these states. Maybe it's easier to find the good policy directly. So in policy search, the idea is to parameterize your policy with some parameters theta, and then directly optimize its performance with respect to these parameters. So typically the performance is expected discounted reward, but there are other formulations, average rate. And I think everything I will mention today applies to these formulations. So one nice thing about policy search is that, at least in theory, it should be able to handle discrete and continuous action spaces basically for free. Because your policy in, say, a discrete action space could just be the Boltzmann distribution. If you want to do continuous actions, it would be simply a Gaussian. And if you can optimize the performance with respect to the parameters, it's the same method. It should. So how can you actually do this? So there's a really simple method known as the cross-entropy method. Slight variations of it go by many different names. It's essentially an evolutionary. And this can be very effective on problems, especially with low-dimensional parameterizations of the policy. So for a number of years, the cross-entropy method was state-of-the-art on Petra's which was a standard benchmark for RL. And there again, the intuition was that actually the optimal value function was quite complex to learn, but finding a good policy was much easier. It took many years for value-based methods to catch up. So how does it actually work? Well, so we start with some distribution over our parameter vector theta. So this can be a Gaussian mean vector mu and some covariance sigma. So then we basically repeat this procedure some number of times, where we first sample n vectors from the distribution of parameters, and then we run each of these policies. So we plug in the parameter vector into the policy and run it for some amount of time. We basically evaluate each of these policies. And then we sort them by performance, which total reward, average reward. And we take the top k forming thetas, and we recompute the mean and variance from these top k vectors. And you might have to add a little bit of this regularization to the variance. But basically, this is how it works. We perturb the parameter vector a bunch of times, run these policies, see how well they do, and then essentially average the best k to get the mean and compute covariance. So again, this can work surprisingly well in low-dimensional spaces, and something similar to this was recently shown to work reasonably well for neural nets and small confidence are, I think, still not nearly as good as the best, well, state-of-the-art methods, but it's surprising that it worked. But of course, you know, this is a pretty naive method. It's essentially just direct search in parameter space. So can we do better? And of course, if our policy is differentiable, then we have access to gradients. And it turns out you can do better by using the gradient information. So we can optimize the performance, try to optimize the performance of the policy gradient descent direct. So now, if you want to do this, the goal is to compute the gradients of our objective, which is expected reward, respective parameters. This might seem tricky, you know. These are rewards, they come from the environment's a black box. How do we do this? These things aren't differential. But it turns out there is a nice unbiased estimator of this gradient. So it's worth going through the derivation in a simple case. So we'll consider one-step MDPs, or contextual bandits. So here you basically have a discrete set of states where the start state is determined some distribution B, and the agent starts in the state and it takes an action A and gets some reward RSA. And then that's the end of the episode. So this is a very simple setting, contextual bandit. So let's try to work through the math a little bit. So if we want to differentiate the expected rewards, you know, we write it out and we have summation over state probabilities, action probabilities. So we can bring the gradient aside, and then we can apply what's known as the likelihood ratio trick, which I think you already heard about in Jan Peter's lecture. So you basically multiply and divide by the policy. I think you basically have to assume that your action probabilities are non-zero, but that's reasonable. And then this thing is actually the gradient, the log probability of the policy. So if we write it like that, then we're actually back to having an expectation. So now what we end up with is, again, an expectation of the gradient log prob of the action times the reward. And the expectation is, again, with respect to the start state distribution and policy. But we have access to the environment. We can generate act in it, and we have access to the policy, so we can sample the policy. So actually, so as we saw, the gradient of the expected reward is given by this, and turns out there's a nice way to basically have a sampling-based approximation. So if we simply run our policy through the environment, generate an action, get a reward, then we can optimize the objective with stochastic gradient, basically doing a Monte Carlo estimate of the expectation. So that's kind of neat because, we started with this thing and it wasn't clear how we could get the gradients of this thing. So that's the one-step case. If you go to full MDPs, the math isn't too different. You can work through it, but basically there is a roughly equivalent result for multi-step. I think this result, comes from the classic paper by Rich Sutton. Basically, in a full MDP, the gradient of the objective is now given by this, where again you have an expectation over the environment and policy dynamics. You have grad log pi times the action value function of your current policy. So this is the policy gradient theorem. So this gives you basically the expression for the true gradient, but in practice we don't have access to the true action value function for the policy. Of course, we saw methods for learning to approximate it, but basically in the multi-step cases and the one-step case, there are easy sample-based approximation. So a classic one known as reinforce, which is due to Williams. I think he had papers, I think as early as '89, results. But basically, if RT is an empirical return from running your policy from state T, then this gives you an unbiased estimate of the gradient of full objective multi-step. So again, this is something we can run. So we can run a policy in MDP, say run it until the episode terminates. We have returns from each of the states, and now we can take gradient steps and do gradient descent on full objective. So that's really neat. So basically, you optimize the performance of policy and gradient descent. So in practice, this can work, but it has quite high variance because you're sampling these returns from your policy and environment dynamics, and depending on the environment, there can be a lot of variance. So it turns out that it's important to use various variance reduction techniques. And if you work through the math, it's pretty easy to show that if you subtract something that depends on something that can depend on the current state, but doesn't depend on the current action or any future actions, if you subtract it from the return, then you don't actually change the expectation with respect to action. So in reinforce, this is known as a baseline. And it turns out that using a baseline can drastically reduce the variance. And one good choice for the baseline is actually the state value function. Yes. And in practice, this is what people tend to use. So you actually do something like following up, which has a very nice intuitive form. So you have this grad log pi term. So what does this do? So you're evaluating the log prob, the action sampled from the policy. So this term is basically saying make the action you sampled more likely. But then you multiply it by this term, which is the difference between the amount of reward you actually got and the value function, which is how much your reward expected to stay. So what happens is if you get more reward than you expected, you will increase the probability of the action you sampled. If you got less reward than you expected, this flips the sign of this term, and you're actually making the action you sampled less. So, this is a very simple, intuitive update, and it actually does the. Now, I think the action value function isn't actually optimal baseline. So you could try and derive something that a minimum variant baseline to use. But it is quite close to the optimum. And learning a value function is a very natural. As we'll see later, you can use it to reduce variance. And right. So can we actually do this with neural networks in practice? So when we were working on DQN, we were wondering, one-step Q-learning is a pretty basic method. Can we experiment with these on-policy methods like policy gradients? Basically, will they be stable? So as we saw in this slide, so according to the policy gradient theorem, you basically need estimates of the action value function. Well, you need to know the true action value function of your policy, or you need samples from true policy. So in DQN, where we had a replay buffer of previous experience, basically doing replay with standard policy gradients isn't something to do, because you need samples from your current policy. And if you plugged in experience from stale policy, different policies, it can and does tend to flow up in practice. So DQN does off-policy learning, and at the time, there weren't really good practical off-policy gradients. So now there are things like this, something like Acer, Z-Wing, others, PGQL, Brendan O'Donnell. So there are ways of doing replay policy gradients. But at the time, we were wondering, how can we apply policy gradients to neural nets efficiently? So what we ended up doing was switching to a different learning framework. So we started looking at asynchronous training of reinforcement learning. So now the idea was to have many agents running on one machine in separate threads. So each agent would have its own copy of the environment, and it would have its own local copy of the network. And it would basically generate experience from this local copy of the environment, generate gradients, and apply them to shared model. So because these are all running as on one machine and separate CPU threads, they have access to shared memory. And communication costs are quite minimal because you just directly apply gradient updates. So in particular, we were doing hog-wild style asynchronous SGD. So we weren't doing any locking on the model. So this might sound crazy, but say in linear models, you can prove that this is a reason. Yeah, it was a little scary to try this with neural nets, but it ends up working in practice. So how can this work? Don't we expect basically the correlated gradient problem to pop up that we had in Feudal? So the thinking was that if we have n workers working in the same environment, that each one might be stuck in some particular part of the environment at any given time. But if we used enough workers, hopefully the overall updates being applied by them would be sort of more spread out across the state space. So this sounds like maybe a little bit of wishful thinking, but you can try and make this more likely to happen in practice. So you encourage the policies to be more different. So you can give, for example, different exploration rates to each policy, so it tends to do slightly. So in practice, this ended up being okay. So now we essentially have this framework where you can take any reinforcement learning algorithm, value-based or policy-based, on or off policy, and just run it in each of the workers. And hopefully we'll have stable learning from parallels. And also, of course, we hope to get training speeds from parallels. So we looked at a number of different algorithms in this frame. So we wanted to try Q-learning because we knew that worked. So this was standard Q-learning where again, you're regressing the Q values towards the one-step Bellman backup. And we would just generate these updates online and accumulate them to a small mini batch for applying to a shared one. The next method we looked at was n-step Q-learning. So here, again, it's the standard Q-learning formulation where you're regressing the Q value, but now the target isn't the one-step Bellman backup, it's the n-step Bellman backup. So for example, if you're in the first state, we would first compute the sum of the next n discounted rewards. So as we saw in reinforce, we didn't want to compute the entire return, because there you have to play until the end of the episode. And maybe in your environment, episodes can arbitrarily long. So then what you can do is just truncate the sequence of n's rewards with a value function. And this is basically reducing the variance over the full Monte Carlo return, but it also lets you stop early and use an estimate of how much reward you expect to get out. So this goes back again to very old work from Yang and Williams on multi-step Q-learning. And another benefit of this is that now you're actually propagating rewards much faster. So if you got a reward somewhere, say for example here, then it won't be just the previous state or the Q value for the previous state that will get updated this reward. You will have basically the Q values of the previous n states will be updated this reward. So you can propagate rewards much faster than step return. So it's also less biased, but has higher variance than one-step returns. But in practice, this tends to be very useful. So n-step returns, as we'll see, end up learning much faster. So the other thing we looked at was, of course, a policy-based method, because that was largely the motivation for starting this work. So here the agent looks somewhat different. So the agent was, well, it can be a recurrent neural network, it doesn't have to. But basically at every time step, you output a policy and a value function. And we do something that looks like the reinforce update for the policy. So here again, we have grad log pi. But now we're multiplying it by the difference between the n-step truncated return and the value function. So this looks like reinforce, but again, we're truncating the return early and using the value function to estimate how much reward you get after this. And this turns out to be a good thing to do because it's a nice trade-off between bias and variance. So the longer the sequence of rewards you use, here the less biased the method. So if you use full returns, it's unbiased. These are unbiased estimates of your Q function. But say if we use a one-step return, that's very biased but has very low variance. And using n-step returns turns out to be quite important policy. So it doesn't actually seem to work in practice with one-step returns, and this is analyzed quite nicely. A generalized advantage estimation paper by John Schul. So he showed that combining returns of different length in your policy grid is important to essentially reducing the variance enough to make this practice. So that's the update for the policy, and then the critic or the value function is just doing n-step TD learning, so it's minimizing the squared, mean squared error shown. Okay, so how well does this actually work? So we compared this to DQN on a number of Atari games, and DQN was running on GPUs, as we discussed yesterday. Asynchronous methods, namely one-step Q-learning, SARSA, n-step Q, A3C, those were all running on one machine on 16 CPU cores without a GP. And specifically here, we were looking at training time. And we found that actually all of these asynchronous methods, well, first, all of them seem to work just fine. So this was somewhat surprising because it took quite a bit of work to get Q-learning to be stable in neural nets. But now we have basically these 4 different methods, both one-step and n-step, value-based and policy-based. And they're all training neural nets just fine. So that was exciting because now I have many methods to so then there were a few interesting things. N-step methods tended to be much faster in practice. Maybe not on all Atari games, but propagating rewards with n-step returns does seem to help. I almost never heard of it before. And somewhat surprisingly for us, we saw that actually this A3C sync advantage actor-critic method often just kept training. So the Q-learning methods would maybe plateau, but this policy-based methods would just keep going. It was basically much better and much faster on many of these games. So that was quite exciting. So then we wanted to look at how well does this scale with different numbers of workers. So here we looked at 7 Atari games, and basically for each game we picked a score that we knew all methods could reach with any number of workers. And then we trained each method with different numbers of workers and measured the amount of time it took to reach this reference. And then we looked at how much faster do you get to the score, say, k workers than with 1. So this is measuring the average speed. So again, there were a couple of surprising things. We saw that for one-step methods, the speed up was actually super linear. So with 16 workers, you were getting over 20 times speed ups, 8 workers, 12, 13. So how is that happening? And with all of them, they were scaling quite well. So with n-step Q-learning, it was linear, and with A3C, it was still quite good. So you're getting further magnitude speed per point, 16. So what's going on here? So we looked at one-step methods to better understand why the speed up is super quick. So here we're showing again training curves for a few Atari games. Here the x-axis is the amount of data consumed by all the workers. Before we were showing time. So again, y is just the score. So here, if we look at the blue curves, which were running one thread, so purely online, and the yellow curve, which is 16 workers, even if when they consumed the same amount of data in total, on some games we saw that you learn much faster or you're much more data efficient as you use more workers. So this really shows that basically, yes, if you do pure online Q-learning on a neural net, you do have this problem of correlated gradients. No, yeah, here it's pure. And yeah, and for each one, we did a hyperparameter search. So we searched for, I think, the right step size. And basically, so you can train these models with one-step Q-learning purely online, but you end up using a relatively small step size usually. But as you use more and more workers, this idea that you can get basically overall more decorrelated updates, or they're more evenly spread out over your state space, This improves the data efficiency, so you can end up using a higher step size. And this was, quite surprising, but this explains why the speed of super linear. So as you add more workers, you make the method more stable and more data efficient, but also because of parallelism, you get through the same amount of data much faster. So they compound, and you end up with the super speed. Now, you probably don't actually want to use one-step methods because, as we saw, n-step tends to work better. And also, I guess, and this effect was less pronounced with n-step Q-learning, which I think we also have some idea of. So why does n-step Q-learning suffer less from basically correlated grade? So I think the main reason is that when you update the Q value, the target is based on the Q value from n steps in the future. So when you change the current Q value, you're much less likely to also change Q value n steps in the future. With one-step methods, you're basically bootstrapping from the next state, which is very similar to the current state. And it's hard for the neural network to basically initially learn to separate, make different predictions for visually very similar inputs. With an n-step method, you're bootstrapping from a much less similar input, and you don't have this interference problem. So n-step methods are also seem to be inherently more stable neural networks. And this effect is even stronger where you're training recurrent neural networks. So we didn't have much luck training recurrent neural network policies with one-step, but n-step Q-learning 3C were quite successful. This. So then we also looked the same plots for A3C. So if you run A3C with different numbers of workers and look at data efficiency, what happens there? And it turns out that for the most part, the data efficiency is almost the same regardless of how many workers you use. And this was again a bit of a surprise because this is essentially saying that you can run this method online at one worker, no experience replay, nothing. And it seems to be currently just fine, stable, you can train your own. Why does this happen? Again, we don't know for sure, but it's probably because in Q-learning, there is interference between different actions. So if you increase the Q value of one action in one state, you will likely change the Q values of the other action the same way. When you're learning a policy, this is typically a Boltzmann distribution over action, so it's normalized. So if you increase the probability of an action, you're not going to increase the probability of all the other actions because it's a probability distribution, it's normalized. It can't increase the probability of all actions. But with a Q function, if you increase one Q value, you might inadvertently increase the Q values of all the other actions. And again, similarly, when you're doing bootstrapping, it's just in A3C, you're learning state value function. So it's just a single number state. So there is less interference. So in A3C, the speed up seems to come purely from parallelism. And it's sublinear, but it's pretty much, I think, up to something like 32 workers on machine. It was worth the extra. Right, so probably shouldn't spend too much time on this. Of course, we looked at Atari. At the time, the things we talked about yesterday, so dueling and double DQN, were already out. So the main exciting thing about A3C was that you could train much faster. So in one day, on one CPU with 16 cores, we were far surpassing the performance of DQN with essentially less hardware, and also DQN trained for 8 days on GPU. So this was really cool because now you basically do research faster, do an experiment in a day, and try way more stuff. And if you trained it longer, so here it was 4 days. In terms of median, it was around the best method, so not as good as prioritized. In terms of mean human normalized performance, it was state-of-the-art at the time. So this is basically 600% performance on average on Atari. The mean is not maybe that interesting to look at because it's dominated by a few games where DQN gets like thousands of percent of human performance. But the exciting thing was that we could now train, again, feed-forward models or recurrent models with LSTMs. And before this was hard. So then we started looking at 3D environments, which are, of course, partially observed. Recurrent neural networks are necessary for building up a history. So here the agent, again, is trained from pixels, and it's only rewarded for picking up apples, and also these orange spindles, which we might see, which would regenerate apples. So at the time, I think this was sort of first 3D first-person navigation agent trained. So, yeah, since then we've been looking more and more at 3D environment. So again, this is nice because it's one method that works on Atari and works on 3D environments. And of course, so we also mentioned earlier that in theory you can just plug in continuous distribution for the policy and train it on continuous control environments. And it turns out that you can do that. So here, most of these are trained from the features, so the joint angles, torques, I think, velocities. But again, it's roughly the same method. You just swap the Boltzmann distribution for Gaussian, and you can train these policies. So again, at the time, I think even at the time they weren't state-of-the-art, but still exciting to see the generality. But no problems. So this is one of the few examples of trained pixels back then. So it's quite low resolution. So that's what you can see. And this was a 3D manipulation task, which was, I think, quite difficult for most methods. I think this is still tricky. So that, I think, pretty much finishes the policy search part. So yeah, now we saw 2 classes of methods, but both can solve quite challenging problems. So I think now I'll try to quickly cover some recent work on making A3C more data efficient, and then we'll talk about what I think are really exciting research directions in the field. Okay, we have, again, value-based and policy-based methods, and they play these games and learn to drive cars in 3D driving games, but they're still very data inefficient. We're still basically looking at millions and millions of frames to train things, and especially in the case of A3C, it's those plots, like comparing it to DQN, the x-axis was time. And that's because it's a very data inefficient method. So doing these parallel updates, asynchronous training, you're essentially throwing away data efficiency for crunching through data as fast as you can. And I think on poor Deatara results, A3C went through something like 1 billion frames in 4 days. PQN in 8 days would do 200 million frames, but it would for 3. So, this is like crazy amounts of data. And it's especially a problem with sparse rewards. So a game like Montezuma's Revenge, I don't know how many people know it, but you're controlling this character, I think it's Panama Joe. And basically, the first reward that you can get is for picking up the ski. And pretty much anything you do, any action you do that's wrong, you die. So it's a very sparse reward problem with pretty difficult exploration. So yeah, how can we do better on tasks like this? Because again, it might seem a little bit contrived, but if you want to, say, train a robot to perform a task, maybe this isn't that unrealistic. So you get a reward when you pick up some object. And you can try to engineer a better reward by saying, okay, first I'll give you some reward for getting closer, and then some rewards for touching the object, and some penalties using forces that are too high. But it turns out, like, if you start engineering these rewards, the optimal policy might end up being something different from what you can. So designing these binary rewards might be easy. For, okay, you're holding the object. And that's sort of easier to get the desired behavior, something that's multi-objective. So how can an agent learn in these kinds of environments? So there's, I guess, a long line of research where the idea is, well, okay, you have sparse rewards, but you also get very high dimension inputs. So what can you do? Learn about your environment. So the question is, of course, well, how do you learn about the environment? What do you learn a model of your environment? What do you do with the model? How can you represent knowledge? So in this recent work, we basically took, I guess, a somewhat direct approach where we augment a reinforcement learning agent with auxiliary tasks, where the agent either has to make auxiliary predictions about inputs and rewards, or solve auxiliary control tasks. So we will define reinforcement learning problems in the same environment space that should hopefully be for the overall. And so the architecture we came up with, we've been calling Unreal, which stands for Unsupervised Reinforcement and Auxiliary. This was a so the idea behind Unreal is to take an A3C LSTM agent shown here and augment it with 3 auxiliary predictions. So we used A3C, but it's not in any way specific to A3C. So any, you can use any, I think pretty much any agent instead of A3C. So what are the different components? So the base policy, again, is an LSTM A3C agent, which gets observations at every step, accumulates state with an LSTM, and outputs a policy. And in the Unreal architecture, this is the agent that acts in the environment. So this is what decides which actions to take. And this is trained with the true reward signal. So then we added a number of auxiliary predictions. So the first type is we added auxiliary control tasks to the agent. So how does this work? So the idea is the base agent is collecting experience, it's putting it into a replay buffer. And now we take, basically, we define a number of different reward signals. And for each of these auxiliary control tasks, the goal is to learn an optimal policy for controlling some aspects of the environment. How can this help your agent? So what we do is we use the same, say, convnet NLSTM, and we output Q values for these auxiliary control tasks from the same network. So the signal that we get from training on these auxiliary control tasks shapes both the convolutional neural net features and the LSTM features of the agent. Now, because it's only the base agent that gets to act in the environment, all of these auxiliary control tasks have to be learned off policy. But actually, that's fine. We can do this efficiently with something Q-learn. So what exactly are these auxiliary control? So the first type is called pixel control, where the idea is to first we divide the screen into a grid, and now for each cell in the grid, we're going to try and learn a policy that maximally changes this part of the screen. So this might seem like a somewhat odd thing to do, but you can think of it as, before you can learn to navigate the 3D maze, you need to essentially know something about geometry of the space. So by learning how to make changes appear in different parts of the screen, what ends up happening is the agent learns basic things like where the walls meet the ceiling, and because that's where most of the changes appear. So off policy, we use Q-learning to update all of these policies at once, and you can do this with something called the convolutional neural network. So it's essentially a transposed convolution that outputs an image of Q values, and you can update them all off policy efficiently. It's not, I think the slowdown in terms of call clock time is maybe 20-30%. So the other set of control tasks we looked at, which I think are actually much more interesting, are called feature control. So there the idea is, again, not to learn to control low-level information changes of parts of the screen, but to look inside the network you're learning for useful signals. So in feature control, we pick some feature layer of the network, say one of the convolutional feature layers, and now we try to learn a policy for optimally, say, activating this feature neuron. So what would that actually do? Well, as you start learning to control, as you start learning to play the game, you might start learning some features that maybe a green detect, that's what Apple says. So you might have a feature that corresponds to green. So now you will basically start learning a feature that's trying to maximize like green at some part of the screen. So basically, as the network is learning features that are predictive of the board, you start learning how to control each of them separately. Right? So maybe you'll have a feature for being at a door. So now you could be trying to learn a good policy to get in yourself. And as you're refining these optimal Q functions, you're basically, again, learning features that are useful for controlling the environment, which should in return make it easier for the agent to control action. So what are the other predictions that the agents make? So the next set of tasks is focusing on the rewards the agents get. So here the idea is to make better use of positive negative rewards. So here the idea is, again, sample data from the replay buffer in a way where rewarding and non-rewarding states are equal. Like, so we sample short trajectories of states that lead to a reward or no reward equal proportion. And we ask the network to make predictions whether this chunk will give you a reward. And again, this refines the convolutional neural net features to better, faster learn features predictive of short-term reward. So why wouldn't you learn this already through a value function? Well, as you start playing the environment, again, you're sampling data from your policy. The first time you pick up an apple might be by pure chance, and it might take a long time to do it. But because this task is simply changing your neural network features, you can rebalance the data. So you can now do a lot more learning with this one reward transition, and you will much faster learn an apple. So here you're not directly updating your policy, so you don't have to worry of policy learning of actual policy. So again, here this is a way to better use of the rewards to learn features predictive of short. And you can do roughly the same thing by essentially doing more learning on the value function. You just simply do more updates of value function n step t, and this encourages faster learning of features predictive long term. So putting it all together, you're basically adding all these tasks that help the agent learn features predictive of environment dynamics and long short-term. And in turn, this should make it easier to learn a good policy, actually. So we evaluated this on a number of levels from this 3D maze environment called Lab. Most of these involve 3D maze navigation, but we'll show a video. So here we looked at the average human normalized performance in terms of data for vanilla A3C and then A3C augmented with each of these auxiliary tasks, and also Unreal, which is basically combining all three auxiliary tasks. So we see that actually, when you put everything together, you get huge speed ups in terms of data efficiency. So to get to the final performance of A3C, you need 10 times less data. So again, I think what's interesting here is that the agent is not getting any extra information than the A3C agent. This is simply doing more learning on the inputs and rewards that the agent already receive, but you're getting massively faster learning. And if you were willing to train for the same amount of data, then you end up much higher performance. So I mentioned feature control, which I think actually is the really exciting part here, because learning to control higher level features of the agent's representation, I think in the long run is much more promising learning about low level. So we tested this on some maze navigation tasks and found that pixel control was slightly better, but feature control still worked quite well. But I think in the long run, again, it's much more promising because the policies the agent can learn by controlling higher level features could be more useful for hierarchical control. So if you actually learn some policy going to explore, this could be really useful for exploration or learning hierarchical policy. Now, yeah, another question might be, well, do you actually need to do this control stuff? Do you need to learn the auxiliary Q function? So we did some control experiments. So something very standard that you might do is train an autoencoder on your input images, where you, again, use your network's concat to encode the image, and then you would ask it to reconstruct it. So this is a standard way of doing unsupervised learning. So when we did this with the agents, so initially we saw that, again, doing this input reconstruction, green curve 3C, initially it learned faster, but then it kind of plateaued and maybe was even a little worse. And so why isn't this helping as much? So what's actually happening is most of the information in the inputs is, I guess, the walls and the corridors, and the rewards are quite rare. So what the network learns to do, it quickly learns to reconstruct the geometry of the room, and then it pretty much learns to remove the apples. It's kind of funny watching it train. So it learns a lot about the environment, but you can see that it's blind to apples. It's essentially making the agent blind to apples because they're rare. It doesn't know that it should care about apples because they work. So basically, input reconstruction can lead you astray. So that's not the best thing to do, at least. So then you could also say, well, again, do you actually need a value function? Can you make just one-step predictions of, say, pixel changes? So the sine curves here are doing that. At every step, conditioned on your action, you're predicting which parts of the screen will change. So these are exactly the immediate rewards that the agent gets. And this actually helps a lot because it's an action condition prediction of what's changing. So this doesn't make the agent blind to rare things because, and most things don't change, so it's not wasting time. Capacity, say, learning to perfectly construct all. But again, if you do pixel control, if you actually learn value functions, so action conditional predictions, how much the low-level features will change, that's the best thing to do. So it looks like there is value in doing auxiliary. So of course, the motivating example was Montezuma's revenge. So this is comparing Unreal with and without pixel control to A3C. So that's the training curve for A3C. It actually does pick up eventually, but you need to train for like billions of frames. But now if you add, say, reward prediction and value replay, after something 60 million steps, you quickly discover it could behave. So the dotted lines are showing best policies, and solid lines are the average of the best 5. And if you add pixel control and pick up a little earlier and maybe learn a little better. So this supports the intuition that actually learning about the rare rewards more will help you learn these environments much more. So quick demo of the agent plan. So this was one of the easier domains where you have to pick up apples and avoid lemons, where it's a fixed layout. So that's essentially a traveling sales problem tree. So these are now the various 3D maze navigation environments for tested different sides. So the LSTM Unreal agent, it learns reasonable policies, as you can see, but it's still pretty far from humans on these tasks. This is because at every episode, the maze is randomly generated. So it can't memorize the layout. It has to learn to essentially memorize. This is the laser tag task where the agent is playing against bots. So it's quite good at some of these relative. And this is a visualization of the internals of the agent. You can see the agent's value prediction, so spikes, sees rewards. You can see the features and the various convolutional feature maps, and also the auxiliary data being sampled. So the balanced reward prediction, pixel showing which areas the agent thinks it changed. Right, so yeah, so that's pretty much everything. I think now I want to spend, I think I still have half an hour and talk about what I think, yeah, basically the really interesting directions of research. So something that I think everyone is talking about now is hierarchical reinforcement. So these DeepRL methods that we've been looking at, say use convnets, they learn hierarchical features in the visual. So you exploit the hierarchy. But just like in the inputs, there is very interesting hierarchical structure in the action space and policy space. And basically the goal of hierarchical reinforcement learning is to discover the structure and use it better learning. So I guess the seminal work in the area is the options work by Rich Sutton going to so they introduced this notion of options, which are essentially sub-policies that you activate in certain states and run them until certain conditions are satisfied. And then you might use, might learn some sort of meta controller acts in terms of options instead of primitive actions. So how could this actually help? So if you have a set of useful options or motor primitives, so that's one good thing that you can immediately see how you might be able to do better exploration. So if you're in this 4 rooms environment, you just take random actions, you're doing a random walkthrough environment. It might be very inefficient for navigating one part. But now if you have, say, options for going to each of the doorways from each of the rooms, then randomly selecting options will basically make you, well, will make the random walk mix match much faster. So you will maybe cover the maze much more easily. So also if you're learning these skills or options, then maybe you will be able to learn much faster by reusing. So if you have a useful skill that you learned one part of the environment, you might apply it to another. Whereas before you have to relearn the optimal sequence of actions. So this is a really promising area, but yeah, there hasn't been a ton of progress because it turns out it's a really hard problem, both in terms of developing good models, but also in terms of what kind of environments would you hope for these things to work. So for example, we haven't seen something that works really well in Atari using hierarchical reinforcement. Maybe because there isn't enough room in these environments for the use of skills. Maybe by the time you discover a useful set of skills, you've already solved the game. But if you think about something like more of a lifelong learning setting, the agent lives in the world and keeps facing new, but say, related problems, then maybe you learn to solve these problems much faster. So I wanted to highlight a few, I think, more promising works in the area. So one is an interesting model that Sasha Vizhnevitz worked on recently, the strategic attentive rider for learning macro action. So here the idea is not to learn full options, which are basic full policy, but to go after learning essentially sequences of primitive actions that you use. So this is a simpler form of options. And this is maybe more similar to motor primitives. And here the goal was to learn them from reward only, so not to hard code goals or sub-goals, come up pseudo. So again, what's the benefit? Well, maybe you can get structured exploration by exploring in terms of motor primitives. But also, as we see, there is this benefit of economic computation. So once you instantiate macro actions, so once you commit to a sequence of primitive actions, you don't need to look at inputs. So the agent is committed to. Now it's essentially not thinking. So how does this architecture work? So it has two components. So one is instead of generating primitive actions of return, it has this plan, which is essentially this. It's an array which is one dimension. It's the number of actions, and at the other, it's the number of times. And this is essentially the sequence of actions you think take current step. And the other part is this commit plan. So the agent decides at which point it will want to update this plan. And essentially, macro actions arise by writing something to the plan and then committing to it some number of steps. So maybe to give you a better idea, this is diagram of the agent. So here we have 5 time steps of the agent act. So this is the action plan, or maybe sort of left, right, up, down. And this is the commit. And again, here the agent had to replan. So it looks at the input and writes a number of steps, updates the plan, says, I will follow this until this time step. And it decides to basically go right. Now, when you go to the next step, the agent is committed to the plan, so it doesn't look at it. Simply rolls this forward, so it shifts the action plan commit plan by 1 step. Now it simply reads out the action committed to. And again, at the next step, it does the same thing. Rolls it forward, takes the action. Now it says, okay, I have to replan it next time step. Time step 4, it basically updates the plan and decides, okay, there's maybe a reward that green pixels, so now I want to go. And you can train this essentially with something like A3C and learn this end to end. So you essentially learn these macro actions implicit by what's written to the plan. So in terms of results, on Atari, this seemed to help on the more interesting games that require a longer-term plan. So something like Breakout, which is very reactive, so A3C with LSTM feed-forward, that works well enough. Right, the LSTM agents is very good there. So there, the straw architecture works well, but it's actually worse than reactive control. It doesn't really pay to commit to long actions. But games like Frostbite, as Pac-Man, which involve longer-term planning, as Pac-Man follows maze navigation, there was an improvement, somewhat substantial. But again, I think the interesting thing here is you can learn macro actions into roughly the same machine that is for A3C. So another idea that's recently been sort of resurrected is this idea of feudal reinforcement learning from Peter Dayan and Jeff Hint. So this is from 1993. And here the idea is that maybe the agent should actually be a 2-level hierarchy. You have a manager and a worker. The idea is that the manager doesn't actually do any work, doesn't act. The manager doesn't act in the environment. All the manager does is set goals for the work. But the manager is the one that gets the true reward for setting good goals for the work. So it doesn't seem fair. Maybe this is an efficient way to structure work. Now the worker is the one that actually acts in the environment. And it gets rewarded just for achieving goals set by the manager. So it doesn't see the actual reward from the environment. So what's interesting here is the rewards might be really sparse, but whatever the goal the manager sets, the worker can essentially always learn about whether it reached the goal or not. So you can have a very rich training signal for the work. And then maybe the worker will learn to achieve a bunch of goals, and maybe these can be options for the manager. So they had some experiments in this paper. I think I still don't understand what exactly they did. But now, basically, people started looking at the key question, how do you actually represent goals and determine if they've been achieved? So I think they did some experiments with some hard-coded hierarchy, hard-coded goals, but can you do this in a more general? So let's think. Reference. So there's a recent paper again from Sasha Vshnevets called Feudal networks for hierarchical. Feudal networks for hierarchical reinforcement. And so he introduced this feudal network architecture, which essentially follows the feudal RL idea. But the key insight is we can define the goals in a shared feature space, which is shared by the manager and the work. So now the idea is we're going to have a convnet that looks at the inputs and produces some feature. Now the manager, which basically sees the inputs at a lower temporal resolution, and it simply just outputs goals for the work. And these goals are defined essentially as vectors in this shared features. Again, the manager outputs goal vectors, and now the worker gets these goals, and it outputs primitive actions that are executed in the environment. And the reward for the worker can be, you can see it as something like the cosine distance between the goal output by the manager and the difference between the current state and the state at which the goal was set. So the goal is essentially the offset that you want the worker to achieve in the shared features. So it's a direction in which the manager wants the work to change the features. And the update for the manager is something like, it's not exactly the standard policy gradient, but it's something like, so you have this cosine distance between the goal you set and where the worker actually arrived, and you multiply it by this reward as well. And so the worker is trying to set goals that the worker can actually achieve, but also lead to it. So again, yeah, this is the reference for the paper. I think it's now on. So yeah, probably looking at details, but this is essentially the high level. Yeah. So what's exciting about this architecture is it's showing some really good results on our 3D environments which require memory. So there are a bunch of tasks which some of them are essentially taken from psychology literature, and these are tasks that rats are trained. So water maze is a classic task. A rat is looking for a reward circular space, and I think it's hidden, so the rat just has to run around. Eventually, the platform goes up. And the next time the rat is placed in the environment, the goal is in the same place, and it has to return to the same place. So the Feudal networks agent is actually able to learn this in 3D pixels. You can see the first trajectory is green. It's basically wandering around and finds the goal. And then the next four essentially take much less time to get to the goal, because they have some memory in terms of where it was. So how does it actually do it? This is showing for, I think, a single start state, just setting different goals by hand, letting the worker achieve. So the goal space that was learned here is go to some offset from the center and walk around the circle. So what the agent basically learns is how far from the wall is the goal, and then it starts walking around circles. So it's not quite optimal, because you would expect it, the optimal policy to go straight to the goal location. But this is a better behavior than vanilla A3. Okay, so another, I think, exciting direction is neural episodic control. This is, again, getting at this idea that a few people have mentioned, that basic neural networks for RL are very slow, data inefficient. So why are they slow? Well, they learn through gradient descent, the parametric model. So if you get a reward, you slightly change your weights, and might be slightly more likely to do the same thing next time. But now humans are capable of, humans and animals are capable of one-shot. So you do something once, and then you're in the same situation, same thing, you remember it was a good thing. So now people are starting to look at this hybrid parametric on parametric architectures, which I think is really exciting. So one recent one from some of my colleagues defined is neural episodic control. So here the idea is to represent the action value function as a table. So this maybe sounds like a step back. We're doing neural nets to get away from people, so why would we do this? But it's interesting because it's a table where the keys are embeddings produced by a neural network, and these are changing slowly. So this is basically the neural network slowly learning the structure of the environment, learning the right representation. But the values that you store along with these keys are Q values, which you update rapidly. So it could be like a prediction of the value, or it could be just an empirical return. So what might happen is, you do something, you get higher reward, you store this into your table of experience, and then you go back and you realize, oh, I've seen this before, and you see that, oh, last time I got a lot of reward, so I know that if I do this again, maybe I should get one. So what's nice here is that the Q values are essentially updated much more rapidly than the keys. And this kind of network can learn much faster, because parts of it, namely its representation of Q values, is learned basically not through slow gradients. So this is starting to work quite well on Atari. So basically, NEC and So MFEC is model 3 episodic control. So I think this is the earlier model. NEC is the model space. These are various RL. So on these games, you start learning much faster, often reach much higher. In the long run, so overall Atari, still the pure parametric model 3 approaches catch up and surpass hybrid. And that seems to be the really interesting research problem. How do you balance these two things correctly? How do you have this quick changing episodic without degrading long-term performance? So the natural idea is that you have a parametric component, non-parametric one, sort of as you play more and more, if you've seen something many times, then you should put it into your network weights, use gradient descent. But things that are new are stored as non-parametric. You could balance these two things out, provide some fast initial learning. That's it. So another really exciting direction is meta reinforcement. So this is again getting at this idea of, how can an agent adapt to rapidly changing tasks? Deep RL is slow. How can we build something to maybe learn a task with a single demonstration? So meta reinforcement learning is this idea that all neural networks with memory, for example, recurrent neural networks, they learn programs. They can discover algorithms. So if the agent is placed, say, in an Atari game, then that's all it learns. It's one task to solve. But if the agent is placed in an environment where you see a sequence of related tasks that are all different, then the agent, the best thing for the agent to do is to try and discover an algorithm, learn an algorithm with the recurrent neural network weights that is much more efficient, top-level RL algorithm you're using to train. So how could you do it? Well, of course, you need structure tasks have to be similar. Otherwise, it will be hard for it to generate. So this is much closer to, I think, humans learn because, we live in this world. It takes years for a baby to learn most things adults can do. But adults, are capable, very efficient, short learn. Don't have to relearn how to walk around the room. So this idea has been looked at in learning to reinforcement, learn chain RL squared, faster RL as well. But, so one demonstration of this, this is from Jane Wang's work. So this is an example of this kind of task. So basically, this is an agent in a 3D environment. It's sitting looking at a screen. So this is basically like a psychophysics experiment. So in each episode, there are two images. One of them is rewarding, one of them is not. The agent has to look at them, shift its view, and if it picks the right one, it gets a reward. And the next trial will be the same two images, but they might change spots. So it has to basically figure out which is the rewarding image and go back to each of the next 10 trials. And then you start over, like two different images. So essentially, you could see each one as a separate reinforcement problem, where I've never seen these two images. But there is the structure that there are just two things. One is rewarding. Remember which one is rewarding this trial. You should be able to solve. So if you train an RNN agent to do this task, you see this is basically 10 trials in each episode. So initially the agent is not doesn't know problems. But after a lot of training, you see that on the first trial it doesn't know what images, but then it quickly figures out that, okay, it's this one, and it keeps going back to it. So now after enough training on similar problems, it's getting essentially perfect one-shot learning on previously unseen instances. Now, of course, this is still very toy because there is a ton of structure. But you can see that basically, yes, the recurrent net is discovering a way of solving these tasks with a single try. Okay, so another really interesting direction is model-based reinforcement. So this comes up a lot. I think, well, many people, I think, still believe huge promise in model. So why is this the case? Well, if you have a good model of the environment, if you have a perfect model of the environment, you can, for example, evaluate inequality just by running simulation. So that tells you immediately that this is much harder than just learning single value functions. If you learn a good model, value false. So that both shows why it's really promising, but also why it's really hard. So why would you want to? Why do you expect to get something good? So many of the tasks we've been looking at are very much reactive, where you can look at the input and through sort of short forward computation, pick the right action. So playing Pong, see where the ball is. But maybe something like Miss Pac-Man, where we're still not that good as pure deep RL approaches. There, if you see, okay, I need to get to this corner of the room, it's hard because to go the right way, you kind of need to have path in mind that lead to where you want to go. So in Miss Pac-Man, there's still hope that, okay, it's the same layout every time, so you eventually memorize for each location how you get. But in a changing environment, if you need to plan a path, basically you need to reason about, you need to plan for how to get to the goal in order to take the right slope. And I think many people believe that models and planning the way to get the agent has to learn the internal model of the environment, learn to plan. So the interesting research question here, I think, is, well, do you learn an explicit model of the environment, where you literally learn to simulate, where you give it a few screens and then sequences of actions and predict future screens and reward. So this, a few people have worked on this. So Jun Oh and more recent Sylvia Chiappa at DeepMind. So now these simulators are extremely good. These are predicted screens for a driving game. So you can roll forwards the environment simulator for quite a few steps for this reason. And it's starting to help in terms of exploration. So you can imagine sequences of actions, maybe pick the one that you'll find the most surprising, some of certain steps. But we're still not seeing huge gains. And specifically, applying planning methods that assume perfect models to learned models doesn't seem to work that well. So the other promising direction right now is learning implicit environment. And I guess I'm somewhat biased to think that this is maybe the way to go. So instead of learning an explicit model and giving it to a planner, maybe we want to embed an approximate planner and an approximate model into our agent and learn them both end to end. So one example of this was the value iteration network, which was best paper MIPS this year. So here you embed essentially a sequence, convolutions, and max pooling operations. And the observation is that, oh, this kind of looks like value iteration. So if your network can generate values and pass them through many layers of what essentially is value iteration, maybe it will be able to plan ahead. And they showed that, yes, actually, on these navigation tasks and 2D images, this seems to. More recent work is the Predictron, David Silver and other colleagues, which is slightly more general. It sort of embeds more of the computational structure have planned and trains it into reports. But it's very promising, but again, we're not seeing massive improvements on tasks. So yeah, this area is hugely promising. Now finally, deep RL for robots. Yeah, there was a very interesting talk of Shal yesterday, and so far deep RL hasn't really made a dent in robotics. There is a lot of exciting work from Sergey, Chelsea, and others. And this work is promising enough that it's starting to feel like maybe there is a breakthrough coming. And now again, I'm biased being working on deep RL because, well, if deep RL is slow and data inefficient, how can it help in robotics where you can't have that many trials? But it looks like there are a couple of promising avenues. So imitation learning is one of them. So there is some exciting work, one-shot imitation learning. The idea here is that you will have a demonstration of a task done by a human, for example, and you will sort of condition your policy. So now your policy, you're not giving it a task purely through rewards. You're giving it images, and it gets a current observation, and then you train a network to interpret demonstration, current state information, to produce the right action. So now you're essentially, you can train this network, you can give it a different demonstration, and hope it will be able to do this with robot, even though it's never been trained this task. So this is, again, maybe this hybrid parametric, non-parametric model, conditioning model, non-parametric. The other, I think, promising direction is this idea of sim-to-real learning. Yes, we can't do that many trials on a real robot, but maybe we can build simulators that are good enough to learn something useful. And then simulators can do as much learning. So there are some examples of this starting to work. So work from Rusu, other colleagues. So this is from real Jacob arm, not Jacob, but basically these are images of a real arm trying to do a grasp task. These are images of sim. And they basically show that if you do a bunch of learning simulator with a specific kind of model, actually do learn some of these tasks on a real robot by initializing the same method. Whereas if you try to run the same algorithm just purely on the real robot, there's no, well, you might break it or exploration. And again, there is more recent exciting work with OpenAI, where they take this step further, where it's taking the idea of data augmentation to extreme. Generate basically views of the task where permute colors, change viewpoints, and train the agent on the and you simulate violence. And this is interesting because these actually look nothing like, well, not exactly nothing. In terms of appearance, it's very different from actual tasks. But in terms of sort of semantic structure, it's the same. But here maybe we're trying to make it look more like the real environment. And I think they had quite a bit of success where you train on a simulator, and in some cases when you run it on a real robot. So yeah, imitation learning, sim-to. I think I will skip this. So thank you for your attention.
for simple children, also, but a simple estimation of step size and stuff like this. This sophisticated theory based on policy gradient also that seem to be showing macro results. Side is any of this theory covered some theory, intelligence, or sample size complexity?
I would say not yet. So policy gradients, I guess you could probably prove convergence to some, yeah, basic drop sizing, training at the right step sizes. I think for certain conditions, in terms of optimality or anything, I think there is hope. I mean, the theory, supervised learning, that's we're starting to get some better understanding, but even there, we're still quite far. Solid state. Yeah, control makes everything hard. So I think it's a really, yeah, exciting work to get theoretical expertise. So, yeah.
So I have more like a curiosity. Talking about, for example, the Unreal Agent framework, how did you come up with that? As in, was it the result of some brainstorming, the best pick among competitors, I don't know, ideas and competitions, or?
Yeah, I guess. Well, yeah, I guess a couple of things. The actual final Unreal thing was sort of combining two ideas that were separate pretty much until like they're done. We didn't want to write two papers, so the pixel and feature control was one stream of work, and then the reward prediction value read. And actually, well, it seemed to combination is quite natural. In terms of coming up, say, pixel control, so feature control is something David Silver is talking about for a while, but our first attempts didn't really work. And pixel control was sort of attempt to step back, where trying to control features which are changing maybe is hard. So can we control low-level features of the environment first, which are sort of more stable? Once that started working, went back to sort of figure it out.
Hello. In the meta reinforcement, you spoke about two images where one of them is rewarded. Is there any pattern to these two kinds of images?
Yeah, so not so really it's sort of on the first trial you pick one, see whether it's the right one. And then the structure is you basically have to remember somehow which is required to turn on.
And this image gets repeated?
So I guess there are sort of like episodes. Say an episode is 10 trials of the same two images, or the same one. Then you change these two images to two different ones. It's the images of and learn, say, one feature per image to actually to learn some feature.
So I understand right? So it's like one trial consists one output consists of 10 trials, and the image which was selected gets repeated in that sequence.
Right.
So many thanks, Volodymyr, actually, for giving such a comprehensive overview of this exciting field of reinforcement learning. We also have some quiz for you from Tübingen.
Thank you.
Let's thank Volodymyr again.